Welcome back, guys. I'm Brandon Tolbert, and today we're talking structural engineering. In the last video, we talked about the cut method, how we could use it to determine the internal forces of a beam member. Now we're going to go do another method. We're going to use normal shear and bending moment diagrams to determine internal forces. So this is another way, another method to find those internal forces, and you need to add this to your toolkit because it's one of the more valuable methods to calculate internal forces. So guys, get your popcorn ready because this is about to be a show. Let's go. Here we go, guys. Today I'm going to show you how to determine the internal forces using bending, shear, and normal force diagrams. So we're using the same problem we did previously. We have a beam member that's end-loaded and it's being supported by a rope. And so if you recall, in the previous video, steps 1 through 3 we used to determine the external forces on the beam, or the reaction forces. So I'm not going to go through this step again, but this is the result of determining the external forces using our equilibrium equations and free body diagrams. So some key concepts we're going to talk about, or I want you to focus on, is the external forces sign convention. It's a little bit different than the internal forces. And then we're also going to cover normal shear and bending moment diagrams. So all I'm going to do is we're just adding 2 steps onto this problem. Step 1, you want to break the forces into XY components. That's the first thing that you do. If you recall, this was a 2-force member right here, so all we need is the geometry and the result force, and then we can determine the X and Y force components at node 2. So if you recall, the hypotenuse right here, this is the rope, this is the geometry, 4 inches tall, 5 inches in the lateral direction. And you can see if we use Pythagorean theorem, we get our hypotenuse. Now we use this geometry and the ratios to determine our X and Y components. This is shown here. You can see that this is our Y component because it's the 4 in the vertical direction over the hypotenuse. We multiply that by the resultant force and we get our force in the Y direction at node 2. The same for the X direction. We use the ratio. Here we have 5 units in the lateral direction. We throw this ratio in there, we multiply it by the resultant force, and we get our F of X at node 2 equal to 1250. And so if we break it down into XY components, this is what we end up with. We end up with a clean diagram right here that we can use to make our bending, normal, and shear force diagrams. So step 2 is to plot the normal shear and bending moment diagrams. But before we do that, I want you guys to know the sign convention. So if you recall, in the previous video we said that the positive sign convention for internal forces is shown in this diagram. For a left-handed cut, our shear points down, our moment goes counterclockwise, and our normal goes out, as shown here. These are positive. Now, if we're using external forces, it's going to be the opposite. You can see here the positive sign convention for external forces is going to be here. If you do it this way, you won't mess up, believe me. And so your normal force is going to point to the left. That's going to be positive. Your shear is going to point up, and your moment's going to be clockwise. Those are positive sign conventions. And this makes sense if you think about it, because if you make a cut right here, if your normal force is pointing out, well, then by the equilibrium equations, you got to have equal and opposite forces. So your normal, positive normal internal force, if you make a cut, is going to point out. So that makes sense, right? The same for shear. If the shear is pointing up here, your external force is pointing up, and you make a cut, your internal shear is going to have to point down to balance those forces. So it corresponds, I know it may be hard to see, but basically these forces, these moments, this moment going in the clockwise direction, well, the internal force moment will go in the counterclockwise direction, and that's considered positive. So in summary, your positive normal points to the left for external forces, your positive shear points up, and your positive moment rotates clockwise. And that's the sign convention we use when we do shear, bending, and normal force diagrams, because we're using external forces to build these diagrams. Okay, so a lot's going on here, but basically here's your your member with all the forces, external forces in their X and Y components. So now when we think about normal forces, we got to look at the X direction forces. So this one would be something we consider in our normal force diagram, and this one too. Okay, so what we do is we use our sign convention. So positive normal points to the left. This is pointing to the right. So this is negative. So on our diagram, we start at negative 1250, and we go to the right until we run into another normal force. Bang, we hit another normal force right here. Points to the left. That's positive. So we jump up 1250, and we hit 0. And that's what you're looking for on each one of these diagrams. You want to end up at 0. If you don't, you did it wrong. So now for the shear components, we look at the vertical forces. So bang, bang, and bang. And if you recall, our sign convention is the positive points up, the negatives point down for external forces. So this is pointing down, so we go to negative 500, and we go across until we hit another shear force. Points up, we jump up 1,000, bang. And now we go across here. This is where we jumped up at. We go across until we hit another shear force. Up here, oh, we hit it right here. We jump down 500, bang. And so we end up at 0. So we know we did it right. And so now our bending moment diagrams, well, if you recall, bending moment is actually going to be the area under the curve of the shear force. And it's given by this expression. This is the mathematical expression. The bending moment along this axis is going to be the integral of the shear forces along this axis. So if you calculate your areas right here, this is just a rectangle, so it's going to be negative 500 times our length times 5 inches, and so we end up with negative 2,500 pound inches. So our area right here under the curve is going to be positive. And so we take 500, which is our height, multiply it by the length of this rectangle, which is going to be 5. And we end up with 2,500 pound inches here. And so since it's the integral, we know the integral of a constant is going to be a linear line. So we start at this node, we start at 0, and we don't have any bending moments, but we do have our area increasing as we move to the right. So it's going to increase to negative 2,500 right here because that's the area under our curve. It's a linear line because the integral of a uniform function over a constant is going to be x. So it's a linear line. Bang. And so now we hit this area. This is positive area. So now it's a linear line too. And we go up 2,500. So if we go up 2,500, bang, we end up at 0. So there we have it, guys. That's how you do normal, shear, and bending moment diagrams. It's that easy. So now the summary of this is we basically determine the reaction or the external forces. And we showed how to do that in the previous video. If you don't recall how to do that, go look at that. And then the next step when building shear, bending, and normal force diagrams is to break the forces into XY components. And that's what we did. We used two-force member geometry to convert our resultant forces into X and Y components, and some of them were already there in X and Y direction. So that was easy. And now it's simply you plot the normal, shear, and bending moment diagrams, and the things you got to remember is you got to remember the sign convention. It's the opposite of the internal force sign convention, and I explained why. And then you got to realize the bending moment diagram is going to be the area under the shear moment diagram. And that's it, guys. If you run across any other moments, you got to add it in here. But that's the simplest case. So there you have it, guys. You added another thing in your toolkit. I hope you learned something today, and I'll catch you on the next video. There we have it, guys. Today you were able to determine the internal force distribution on a member using normal, shear, and bending moment diagrams. So add that to your toolbox because it's used to determine worst case stresses. But guys, I'm going to leave you with this. Continue to work hard. If somebody tells you to not work hard, they're bluffing. Keep it amped up, keep sprinting, keep getting better. So guys, I'll catch you in the next video. Y'all have a good one. Adios.